Hey guys, in this video we're going to talk about switches, shorts, and failed resistors. First, a little bit of circuit notation. This right here is the symbol for the switch. And so below, what you're seeing then is a simple circuit with one resistor, a battery, and of course the switch that turns that resistor on and off, if it's, say, something like a light bulb. The short, of course, is basically just a bare wire, which in all of our diagrams, bare wires have a resistance of 0 ohms. Now, when you connect up a bare wire in parallel with a resistor, the effect is going to be that the resistor no longer receives current. Normally, what you have is the total current which comes out of the battery splits at the junction according to some kind of a ratio. However, if this path contains 0 ohms, then instead of splitting by a ratio, the resistor just gets skipped. No current flows through it at all. And so if it were something like a light bulb, the result would be it would turn off. In some ways, this is a little bit like a switch, but the difference is with a switch, the current stops flowing. In this case, the current keeps on flowing, which can actually be hazardous and start fires and stuff. A failed resistor could be thought of as something like a burnt-out light bulb, and effectively that makes it be infinity ohms, which should make you think of the whole Christmas tree light thing, right? If you've got bulb, 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 etc., and any one of them burns out, whether it's the one in the middle or either of the ones on the ends, they all are going to turn off, and you have to figure out exactly which bulb is burnt out, which can be kind of annoying and tricky. And so if we had a circuit like this one with a failed resistor in it, the resistors, any resistors in series with it, will also shut off because no current can pass on that path anymore. So that means this one would shut off. The other two resistors would continue to operate, but their brightness might be different than it was before. That is, assuming we're talking about light bulbs. So let's consider an example with a switch and a short. This, I think, might be example 9 in your notes packet. This diagram also contains another circuit symbol that you might not be familiar with, which is the amp meter, which is that right there. Or ammeter is actually how it's pronounced and written. An ammeter measures amps, so measures the current. Now, given that the amp meter measures 1 amp when the switch is open, and given that it's a 60-volt power supply, we're supposed to find R. So go ahead and pause the video and see if you can figure out what R is supposed to be. And there we have it, 20 ohms. Now, however, the switch is closed. Now, if the switch is closed, that's going to change the equivalent resistance of the circuit. So see if you can figure out, based on what we said, what's going to happen to the equivalent resistance based on what happens with the 2R. That's right, the current skips the 2R because it's in parallel with a short, with a bare wire with 0 ohms of resistance. So the current instead only passes through the R and not the 2R at all. So recalculate the current, and we find that the current has tripled through the one remaining resistor R, whereas it's gone to 0 through the 2R. Now, if you're thinking you'd like to see what happens when a bulb gets shorted out, we're going to take a look at that in this video right here. Now, of course, what you should be able to see to begin with is those two bulbs are in series. They are in series with each other, and they are equally bright. But what I'm going to do in a moment is move that blue connector and short out the bulb that's on the red wires. Okay, so the bulb that gets shorted out turns off, but look at the other one. It gets so bright. That's because the resistance is decreased when we short that one out, and therefore the one remaining bulb gets a lot more current passing through it. This can actually result in that bulb failing, meaning burning out, as in the failed resistors that we discussed at the beginning of the video. All right, now here's some practice. This is going to be a symbolic problem. We're going to find the current and the voltage for each bulb first with the switch open, and then you can imagine part B is going to have us calculate it when the switch closes. Okay, so if you like, go ahead and calculate and run the video and pause as needed. Of course, with the switch open, you ignore the whole right branch. So it's really just those resistors 1, 2, and 3 for a total of 3R, making the current EMF over 3R. So we fill in that for the first 3 resistors in the table, and of course 0 for the other 2, because the switch is still open. Now to find the volts used by each of those resistors, we use Ohm's law again, and plug in the current and the resistance of each resistor. And so we'll get EMF over 3 for each one, which is sort of not surprising, right? If each one uses EMF over 3, that will add up to the whole EMF of the battery. Well, now that we've got the table for the open switch filled up, let's try for the switch being closed. If the switch is closed, that's going to change the equivalent resistance, which is going to change a whole lot of other things. So again, pause, see what you can calculate. A partially simplified circuit diagram gives us this. And slightly more simplified, the 2R and the 2R in parallel will give us 1R for a grand total of 2R for the resistance. Now, interestingly, by adding a parallel branch, we actually decreased the resistance. If you recall, that's the way it usually goes. Adding things in parallel makes the resistance smaller. And so if we've got smaller resistance, the current goes up to EMF over 2R. But that's the total current. Most of these resistors do not receive the total current. In fact, only the resistor which is in series with the battery receives I total. When we get to the junction, the current is going to split. Now, normally we'd have to do something like a loop equation to figure out what the current in each of these resistors are, but in this case, because there's equal resistance on these 2 branches, we can just say that I total splits evenly. So resistor 1 receives all of the current, and all of the others receive half of that, because the current splits up evenly between the 2 branches. And once again, using V equals IR, we can determine the volts used by each of the various resistors. All right, now the interesting bit. What does that really mean in terms of what happened to each of the various bulbs? Some of them get brighter, some of them get dimmer. And what you probably should be looking at would be what happened to the current or the voltage. So look at how those change, and then think about what that will mean in terms of the power use of each of those bulbs, since power is brightness for a light bulb. So pause, give it a think, which ones got brighter, which ones got dimmer, see if you get the same answers as me. Yup, bulb number 1 definitely gets brighter. EMF over 3R is smaller than EMF over 2R, and so that means the new current is larger, and so is the number of volts that that bulb is using. All right, and so therefore it's going to get brighter. Even though the total current went up, though, because it was now split along 2 paths, 2 and 3 get dimmer. Oh. And of course, not to put too fine a point on it, 4 and 5 definitely get brighter because, of course, they turn on. Okay. Now, once again, I thought I would build a real version or a simplified version of the circuit that we looked at in the previous example. Nothing's connected up right now, but this particular light bulb is the series light bulb, right? It's in series with the battery or the power supply here. And what I'll do first is I'll connect these two and leave this bulb out of it for the moment, all right? And so as soon as I connect them up, current's going to start to flow, and that one's going to turn on. And these 2 bulbs should be equally bright, since they're same type of light bulb and are going to get the same current. And that is indeed what we see. As soon as we connect them, they are equally bright light bulbs. All right, now make a prediction based on what we should have just learned. What will happen when I connect these two, and now I add another bulb in parallel with this one? And as predicted, the series bulb gets so bright because whenever you add parallel branches, the equivalent resistance goes down, and the series bulb receives the total current. So now it's so bright from all that extra current, but since the current had to split two ways, the two parallel bulbs get so much dimmer. Now you can observe that in real time happening as I unscrew and screw in the light bulb. Right? Rather than disconnect things, screwing it in and unscrewing it achieves the exact same effect. Cool. I thought we would conclude by doing some what are basically logic problems with failed resistors, where the goal here really is just to predict whether things get brighter or dimmer, or say also go out when a particular bulb fails. Now, the reason I say this is a logic problem isn't because you couldn't calculate stuff, right? Remember, the idea is if, two resistors in a series, one of them fails, the other one also goes out. But if they're not the only things in the circuit, right? If there's other stuff connected up, well, then those other bulbs are also going to be affected. And the way that you can predict how they're going to be affected is by using what you have learned so far about equivalent resistance. So feel free to make up numbers here and recalculate and see what happens to the circuit. Eventually, you'll get really good at just predicting things based on the results that you keep getting over and over. So feel free to make up numbers for it, or if you feel like you can logic your way through it, go ahead. So to begin with, what happens if bulb A fails? Well, of course, it goes out, so I've gone ahead and filled in there. But what happens to B, C, and D if A fails? Take a moment to think about it, and then resume. So in this case, if A fails, everything else turns off as well. And the reason for that is because A is the only resistor, in this case, which is receiving the total current coming out of the battery. So if A fails, literally no current can flow, nothing. And therefore, all of the others shut off as well, because no current can even get to them. Now, what about when B fails? How are things going to change when B fails? In this case, some things will get brighter and some things will get dimmer. Some things will go out. Nothing will be unaffected. Okay, that's actually never going to be a right answer choice. So again, pause, think about it, and then resume. Now, the way this works is if B fails, then C also goes out. All right, done, right? If they're both in series with each other, then whatever current was supposed to go through B won't make it to C because B is shut off. So the whole branch is dead. Now, the way to think about what happens to A and D is probably recalculate and see how it goes. A sort of a very shoddy way of reasoning through it, though, would be this, though. Well, some of the current that would have gone through B and C will get diverted to go through D. So the current going through D ought to increase. However, not all of that current is successfully diverted. Some of the current just dries up, and therefore, that's the total current. A will now get less current because of the dried up current that is no longer passing. So A gets dimmer, and D gets brighter. So now what about if resistor C goes out? What will happen then? Well, it's actually going to be the exact same result. It really doesn't matter if B fails or C fails. In either case, both of them are going to turn off. All right, and so the result is identical. All right, now finally, what if D fails? So again, pause the video, make a prediction. What do you think is going to happen if D fails? How are things going to change for the other bulbs? And yeah, we get a similar result. If D fails, then some of the current that was going that way instead now goes through B and C. So those ones will get brighter because more current is now going that way. But since some of that current that was going through D effectively dries up, disappears, the total current is now less. And since A was getting I total, it's now going to be dimmer. All right, and that should be everything you need to know about switches, shorts, and failed resistors. Thanks for watching.